complicated in nature, but what is here that you will see very simple approach how to deal with how delicately you can deal with the convexity of those functions. So it is all about that presentation, and there is a very interesting kind of book by Stephen Boyd on convex optimization. You can see a lot of interesting theory there. Also, you can find video lecture of Stephen Boyd there in YouTube. It is freely available. You can see that video. For that you have to be very good in mathematics, so that's way. So we are starting today's lecture. It is lecture number 33, and here we will discuss about convex function and its calculus. That means how we can extend our class of convex function through various composition like conic combination, like many other kind of criteria will come. Some kind of algebraic tools will come. You will see it here. So coming to outline of today's lecture, first I would like to say that I will discuss about convexity of a function, and then I will give a geometric pattern of what is it is convexity of a function. It happens to be a geometric object. That means when someone is saying that this function is convex, you are able to visualize the convex pattern of that function. So very much clear. It is convex word itself. It is a geometric, and someone is saying a convex. It is a convex function. Simply just put in your mind that that function happens to be very easy to handle for you. That means if you are looking for optimization for that function, easily you can optimize. There are various algorithm, depends upon what kind of problem is there, whether it is constant, whether it is unconstant. So it depends upon that various algorithm are coming. So you will see that algorithm, if you are trying to understand the success of that algorithm, you need to know the convexity pattern of that function. Okay. After that, I will talk about calculus of convex function. That means how you can increase the class of convex function more by adding various algebraic operation like conic combination and other kind of things, what I told. So we'll see those things here in this lecture. Okay, so coming to convex function, what is convex function? So if you ask convex function geometrically, it is very simple to see that how you see. So you are having a function in such a way, if you draw first order approximation of a function at any point, then that first order approximation, it would be under estimator of that function. That means if you draw a tangent to function at any point, tangent we can draw it. What is tangent? Tangent plane that happens to be first order approximation of that function at any point. So if you draw, then it would be always, the function would be always above the tangent plane. That one is geometrical definition of what we call it convex function. That means this one is the tangent plane. It is not a proper drawing. So you can easily see that if you draw for this function, this is a very nice kind of quadratic function, x square y equal to x square. If you try to see this function, if you draw tangent at any point, you can draw at any point, you can check it. Suppose you have drawn tangent at any point, so at every point function is above the tangent plane, above the tangent line. If you are in 3D structure, it would be tangent plane. If you are in 2D structure, then tangent line. So it would be always above the tangent. Simply I would like to say that. So that's where this function happens to be convex in nature. That one is one geometrical, that one is coming from first order approximation. Another one is saying that if you take any 2 point on the graph of the function, so this is the graph of a function. So if you are having a function f of x, so what is meaning of graph of the function? You might have always seen the meaning of graph of function means it is collection of the order pair x and fx, x and fx, and x is coming from the domain of the function. So this we are calling it graph of the function. That means it is talking about this is the graph of function. Geometrically, if you see, this is the graph of function. Algebraically, in set theory form, how we write it like this way. It is the collection of all order pair x comma f of x, such that x is coming from the domain of the given function. Suppose D the domain of the function. So this one is algebraic representation of the graph, and this one is geometrical representation. So if you are having a graph of the function, what we do, take any point on the graph. That means take any 2 point on the graph. Take, suppose if you are taking one point here, another point here, so one point here, name this point. This point would be what point in the graph? It would be x comma f of x. Okay, and you are taking another point here. So what would be name of this point? Give name of this point. It would be y comma f of y. Okay, so 2 point on the graph we have taken, and line join the second. Second is the what? It is a line segment joining these 2 point on the graph. So we are joining these 2 point on the graph, and we can observe that the segment of the graph which is always behind this line segment. So if you are having a function which is satisfying this criteria, that if you take any 2 point from the graph and the function part between those 2 points always lie below the second joining those 2 points, then we can claim that that function would be a convex function. If we suppose if someone is willing to take the point, 1 point here, another point here, then what would be second would be something like this. It would be here like this. Again we can say that this portion of graph, it is always behind this second. So always such criteria is coming. If you someone is taking point here and here, any 2 point here, again we can observe that this segment of the graph is lying behind the line segment joining these 2 points. So overall we can say that the given function, it is a convex optimization problem, and so it is a convex function. And I have already described definition of convex from several perspectives. I have already defined. So first actually we will go for that algebraic definition of convex function, then we will talk about geometry. So what does algebraic definition of a convex function say? Suppose that we are having a function of several variable. It is defined from Rn to R. Okay, then this function would be convex. Then first criteria is that what domain of the function must be convex. This one is the what first essential criteria for defining a convex function. And domain of a function, it would be a set, and we know the convexity of a set, we have already defined it. So we are all aware of convexity of a set. So after that we are defining convex function. So before defining a convex function, we have to take a convex domain, okay, of the function. Apart from that, we need to see another property that we are calling it every line segment or image of line segment, or geometry, what I had already told, that this one is saying that if you are taking any 2 point from the domain of the function and you do perform a convex combination of these 2 points, you can say that this one is the convex combination of these 2 points. Then what will happen, that image of the convex combination always less than equal to the convex combination of the images. Here remember that this I am saying that image of the convex combination, that means functional value of f at the convex combination of x and y, any convex combination of x y is always less than convex combination of the functional value at x and functional value at y, always less than. Same, it is algebraic definition of convexity of a function. So what geometrically it say that this, what is this, just focus on this inequality is the main part of defining a convex function. This domain being a convex, just it is an what essential requirement, but the convexity of a function, it is established by second condition, that this is the second part, is the most important part of the defining the process of defining convex function. So geometrically, what does it mean? Geometrically, this inequality means that the line segment joining the point x, uh, any 2 point on the graph, this point x comma x, f of x, I told that it is a point on the graph, and y comma y, f of y, that one is also another point on the graph. So if you are taking any line segment joining these 2 points on the graph, it must sit above the on and above, you can put on and above the graph of the function in that segment only. Okay, so that is the geometrical meaning. If you want to see further geometry, then you can see it like this way. Suppose we can see that we are having a function like this way, and what this one is talking about graph. I told that what is the notation of graph of a function? We always take collection of all the order pair for every point from the domain of fx, order pair x and fx, such that x is coming from the domain of the given function. Okay, so this will define graph algebraically. Geometrically, you can visualize this curve is the graph. Okay, geometrical visualization. Algebraic one is this one. So in this graph, we are taking any 2 point, x and f of x, y comma f of y, and join these 2 points by this line segment. So what is name of this line segment? If you want to see, name of this line segment is theta f of x plus 1 minus, it is just a convex combination of the given point on the graph f of y. This is the equation, this is the equation. Okay, and here what is the condition over theta? Theta must be between 0 and 1 in order to define a convex combination. It may be 0, it may be 1. So it lies between, theta is taking value between 0 and 1. So this is the line segment. Simply it is talking about, it is a line segment joining the point x comma f of x and y comma f of y. Now in this region of x, we can observe that this portion of graph, it is always behind or below the line segment joining this point. So that means this is for one single theta we are getting that this linear convex combination, it would be somewhere here. Suppose it would be here, it would be here. Then what, where is the value of f of that convex combination of x and y? So that would be here corresponding. So you can put it like this way. And so here, what is this point? You can denote it by this one, theta times f of x plus 1 minus theta times f of y. And what is name of this point? This is image of convex combination of x and y. Theta times x plus 1 minus theta times y. Likewise, you can see all these scenario. You take any point here for some theta. Here theta would be something, here for, and here theta would be something. So for that, again you will see that this point would be theta times f of x plus 1 minus theta times f of y, and this point would be f of theta times x plus 1 minus theta times y. Okay, this point, same scenario. So you can call it here, suppose this point is theta 1, you can put it theta 1, but theta, again theta 1 would be between 0 and 1. Then this point you can give name, and this point would be theta 2 with respect to theta 2, another value of theta from the interval 0 1. Likewise you can define it. Now then if a function is convex, we are defined like this way. Geometry is like the line segment joining the points on the graph, always above the value of the function on the graph, above the graph we can say like in this way. Okay, so this is definition of convex function. If we are having a convex function, then definitely there would be also non-convex kind of function. So what is non-convex function? That means a function which is not satisfying this inequality, which is not satisfying this inequality somewhere in the domain, then simply we can claim that that function is not a convex function. Like one example I have taken it here. So we have taken this polynomial kind of function, very zigzag in nature. You can observe that this function, you can observe that here, if you observe from here to here, this function looks convex and there is no issue. But if you look from here, so if you take any 2 points on the graph, one point here, another point here, and join the line segment, then you will see that the function value, this portion of graph, it is above this line segment. So we can say that it is not satisfying the above criteria, inequality criteria. So what, this function is not a convex function. It is not a convex function, or simply we can say that non-convex function. This one is a non-convex function, and the first one is a convex function. This one is what? It is a convex function. That is the definition of convex function and non-convex function, and it is very simple. It is having a clear geometry. It is a convex function. Okay, now I will talk about further, not it here, affine combination. I told that I will talk about another kind of convex function. That one is a strictly convex function. What does it meaning of strictly convex? It is same convex, only difference is coming. Everywhere definition is same. That domain of the function must be convex. And in second part, in the case of inequality, what we observe that in place of less than equal to, we are observing a strict inequality. So in the inequality part, in the definition of convex, if you observe strict inequality, then corresponding function we are calling it a strictly convex. So a strictly convex it is very much needed. We will see that we need to see the difference. It is more a stronger version of convex function, and even one more which would be stronger than this stick, that we will see it, that we will call it a strongly convex function. So that also we will see it varies. So I am taking one example. So this function, you can say that this function definitely it would be a convex function, but this function is not a strict convex. Why? There is a very simple kind of test to identify whether a given convex function is not strictly convex. What is that? That if you somehow you come to know that there is any line segment part in the graph of the function, anywhere line segment part, then you can simply claim that the function would be convex, but would be not a strictly convex function. There would be no strict inequality. Okay, so like this function, if you plot graph of this function, what we observe that, so here a strict inequality. So if you talk about domain of the function, if you restrict up to minus like this, with this nature, this kind of nature, then we will say that this function is not it is it is stick as well. If there is a curvy nature, if you see simply see line nature, so here this one is line, this one is line, this one is line, all are linear part. So we can say that this function is what it is convex, but it is not strictly convex. Why? Because if you take any two point from the graph of the function and join the line segment, this line segment of this line segment, it would be equal to the value of image of the convex combination of any two point from the point. So here equality directly here, if you take any point here also, so here directly we observe here what equality we observe here. That means f of for any theta or any x and y, any pair of point, we observe here equality f plus 1 minus theta times y image of convex combination of xy is equal to a convex combination of corresponding images. I would like to say that theta times f of x plus 1 minus, okay, 1 minus theta times f of y. So equality we observe. So here there is no strict inequality. So this function is a convex function because we know that what is meaning of less than equal to? It says that it implies that, and implied by that it is either less than or equal to two sign it is containing. So here it is true. So from that perspective, inequality less than equal to, from that perspective this one is true. That's why this function is a convex function. But if you talk about a strict inequality, this function is not a strictly convex. It is, why? Because it is not satisfying a strict inequality anywhere here. So this one is a convex function, but not a strictly convex. I'm taking another example here. So this function, you can observe that this would be strictly convex due to curvy nature. So you can observe that if you take any two point anywhere here, say here, if you take here any two point of the graph and join the line segment joining these two points, what we observe that we can observe there here a strict inequality, because this much of graph is strictly below the line segment joining those points on the graph, strictly below. So and hence we can say that y equal to x square, it is strictly convex. Convex and a strictly convex. A strictly convex is more stronger property than convex. So that's where here we see. Now I will talk further about another variety of convex function that we are calling it a strongly convex function. What does mean a strongly convex function? So what you do, you take a function, okay, take a function and truncate one quadratic part from that function. After truncating a quadratic part, some scalar multiple of quadratic part, if you are truncating from that function remain again a convex function, then we will say that such kind of function is a what we call it a strongly convex function. So if we can define it like that, a function, it would be a strongly convex function if first criteria is domain is must be convex, and second criteria that if you truncate a quadratic part from that function, then that function is again a what convex function, it remain a convex function. So that is the definition. So geometrically further, algebraically further, if you want to explain, you can write it like this way, the definition of a strongly convex function. So if someone is saying that, oh, can you give a example of function which is not a strongly convex but convex? So one example is coming like that, e to the power minus x, or e to the power, if you take e to the power minus x, so what will happen if you take what is the plot of e to the power minus x? When x is approaching to infinity, the exponential function will approach to 0. So here what will happen, keep on going. So here it is what this much of this function e to the power minus x, it is asymptotic to x equal to 0 at infinity, asymptotic in nature. So that's way, if you truncate a quadratic part, you are truncating a quadratic part, that big much of amount you are truncating from it, and hence no more if after truncation it would be no more quadratic convex in nature. If you after very high value of x, then if you truncate it would be, so this function is strictly convex but it is not a strongly convex. So a strongly convex is more stronger than strictly convex. So that I would like to say that. So here generally here again same thing I would like to say that. So if f of x, you are taking a function which happens to be a strongly convex, and if you truncate one some amount of quadratic part from this function, then what will happen, that again we observe that the truncated version is again a convex function. Then we can claim that this function is a strongly convex function. So a strongly convex function is very interesting kind of thing, that if you are taking x square, okay, f of x equal to x square, if you are taking and truncate one quadratic part of x square, so few one quadratic part, that means you truncate it by x square by 2, then remaining would be what, f of x minus x square by 2, what would it would be, it would be x square by 2. So that x square by 2 is again a convex function. So that's way we can say that yeah, we truncate it by subtract x square by 2. So we are subtracting it, this function x quadratic function by x square by 2, then remaining would be what, it would be x square by 2, some amount of quadratic function we are subtracting. So again after subtraction we observe that it remains a convex function, x square by 2 is again a convex function. So we can claim that this function is a strongly convex function, a strongly convex function, this function. So that I would like to say that. And another example I have given, this one is this one is strictly convex but it is not a strongly convex function, e to the power minus x, and even 1 by x, if you take, there are various those functions which are having asymptotic nature, simply you can convex functions which are having asymptotic nature, those falls in that category. So a convex function may or may not have a minimizing point. If you are taking a convex function, then it may or may not have a minimizing point. But if you take a strongly convex function, it will have a unique minimizing point. So for example, if someone is saying that anyone may give an answer, what is the minimizing point where this e to the power minus x is having least value? Anyone may answer, what is the minimizing point of e to the power minus x? That means what is the minimizer of e to the power minus x? Anyone? Everyone have gone through that math 1 class, no? Tell me, what is the minimizing point of e to the power minus x? Okay, Kalpjit, would you like to answer? What is the minimizing point or optimal point or minimum point for e to the power minus x? Yeah, it tends to actually minimum value is approaching to 0, but minimizing point is approaching to infinity. Yeah, so we don't have that, infinity is not a point, so infinity we can't say that it is a real number. That means simply e to the power minus x is having no minimizing point, no optimal point or no minimizing point, that answer. But e to the power minus x is a what, it is a convex function. Even more than that, it is a strictly convex. Despite of being a convex, we don't observe any minimizing point. So that's way a strictly convex function is not of much use regarding unique solution. A strongly convex is always important. So here, nice try. So okay, so if you take a strongly convex like this kind of function, so it is having a minimizing point. Where is that minimizing point? It is here, it would be at this. So this a strongly so every, if you take any kind of a strongly convex function, definitely that function would have a unique minimizing point, and hence you will get an, if your criterion function happens to be a strongly convex function, so you will say that okay, I am having a unique optimal model with respect to that criterion function. So that's way, while efficiency test, I had taken, or we had taken mean square error as a very in defining mean square error, we had taken the criterion function as a quadratic loss function. Why? Because quadratic function always happens to be a strongly convex, so it will guarantee unique existence of minimizing point. So that's why we are taking a square error, a square of error function, a square of error, that means quadratic function we are taking in order to get a unique minimizing point or unique optimal point. Both are same name. Now I will talk about further geometrical uh, characterization of convexity of a function from the perspective of epigraph approach. So epigraph is simply, it happens to be a what set approach, that till now we have seen geometric structure of convexity of a function. Now onward we will see that definition of convexity of function will be translated into again definition of convexity of set. So that concept is coming through epigraph. So what is epigraph? It say that, so suppose we are having a function f. So simply I told that if you are having a function f, then what is the graph? Graph, it is the, algebraically we say that it is the collection of all the order pair x and f of x. So for every x, that one is coming from domain of f, then this we are saying that it is a graph of the function f, graph of the function f. And where would be, if f is having domain in n dimensional space, then where graph will go? It will go to n plus 1 dimensional. Like if you are taking function of one variable, uh, f of x, where x is coming from real number, then graph, if you talk about graph, where does graph will go? It will go to R2. It belongs to R2. It is the member of R2 when you are taking function of one variable. That means here you are putting a criteria that x is coming from real number just. That means f is a function of one variable. In that case, graph is what? It is a subset of R2. It belongs to R2 or subset of R2, simply we can say that. So due to that, if you are defining a graph of a function, what we do, it do a dichotomy, that it divides complete that n plus 1 dimensional plane a space into two part. One part we are calling it epigraph, another part we are calling it hypograph. So that division we see it here like this way. So epigraph is what? The epigraph is the portion of the that space which is above on and above the graph, that we are calling it epigraph. Algebraically how we denote it? That means it is the this order pair x comma t, such that it is a all those point for which t is greater than equal to f of x, that above part of the graph, above part of the graph in the uh, n plus 1 dimensional space. Okay, and what is the hypograph? Hypograph is the section or part of the, what we call it, a space which is behind the or below the graph, below the graph. So I'll always do dichotomy. It is similar to what we had already discussed about what do the separating hyperplane do, or what hyperplane do. It always divide the given linear space into two part. One is upper half of space, another one is lower half of space. Same thing is done by a function. If you're taking function, then graph of function always divide the corresponding n plus 1 dimensional space into two part. One is epigraph, another one is hypograph. So geometrically, if you want to see, it is coming like this way. So suppose you are having function of one variable, and this is the black line, black dark line. It is a what? Graph of the function f. So what we observe, that this graph of the function, it do dichotomy of R2 plane. It divide into two part of the that complete R2 plane. So this above the part, the segment which is above the graph of the function, that we are calling it epigraph, and the portion which is behind the graph of the function, we are calling it hypograph. So you can easily geometrically visualize like that. So here, if you, what is happening here? So a function would be what convex if the corresponding epigraph happens to be a convex function. So if you take this function first example, it is not a convex. Why? The corresponding epigraph what we are getting it is not convex. Why? Because if you take one point here, another point here, and if you join the line segment, it is not remaining in the epigraph, it just goes to hypograph. That's why this function is not convex. It is not convex. Because why? Because here epigraph is not convex, so that's why our function is not convex. If you take second example, here, we have taken a graph function like this way. This segment is epigraph. Just we focus on epigraph, take any point on the epigraph, any 2 point on the epigraph, and join the line segment. It would be always in the epigraph, and hence we can say that a function which is convex if and only if the corresponding epigraph is convex set. So here we can observe that it is a convex function. Here why? Because the corresponding epigraph is a convex set. So we can say that the function would be a convex function. Okay. Likewise, if you take this example, this function is not a convex function again. So if you take any 2 point from here to here and join the line segment, it would be not in the, this line segment would be not in the epigraph. It goes to hypergraph, but points are in the epigraph. So that's why this one is not a convex. But what is this one? This one is concave. It satisfied definition of concave. So I won't cover concave much, not much, because theory are having similar theory. That means if you are taking function f, okay, if suppose this function is convex, and then it will imply that if you take negative of that function, then negative of that function would be convex, and vice versa. If you taking, if this function f is a concave function, and if you take negative of that, then negative function would be convex. So that's why if you study just convex function, study only convex function, and similar theory you can derive it for concave function. So that's why. So here our area of interest is like this way. Why? Because in most of that learning problem, always you want to minimize some kind of criterion, some kind of error you want to minimize. So minimizing is very much suited term with respect to convex function. Like you can easily geometry, you can see that this one is having unique minima here at this point, so minimizing is possible. But if you proceed with concave function, there in case of concave function, maximization is very easy. So if you are dealing with any term where that if you are in sub factory, you want to maximize your profit, then your objective function should be a concave function. It would be very good for such kind of problem. But if you are going to minimize some kind of error criterion, some kind of thing, then better to always proceed with convex optimization. Okay, so convex, you have to take convexity into picture. So that's where that is the process. Okay. So now in next part of this lecture, I will talk about calculus of convex function. So before going to calculus of convex function, I will give a few more what we call it first order and second order characterization of convex function. Like suppose our function happens to be enough smooth, that means the function, given function happens to be differentiable, then from the differentiability pattern we can directly conclude that the function would be convex or not convex. So that kind of result we will talk about. So first I'm talking about first order characterization. That means suppose function is first time differentiable, then can we say anything about convexity of that function? So yeah, we can say that initially I had already explained that if function is first order uh, what we call it first time differentiable, first order differentiable. So what is happen that in that case, if you try to approximate function at any point by first order approximation, Taylor's approximation, then that first order Taylor approximation, it will provide underestimator of the given function. That is the characterization. So here if f is any convex function, if and only if f of y would be always greater than equal to this tangent plane or tangential line, okay, for any x and y from the domain. So it would be, that means simply it says that geometrically it says that function is always on and above the tangent plane. This is the equation of tangent plane, say on and above the tangent plane. So geometrically I have already written that it is this one is what it is, a tangent plane, and where it is touching the surface of the graph, it is touching at point x. Okay, and this tangent plane, one kind of thing that you can say that the tangent plane is providing a global underestimator of the function. Estimator, the underestimator, that means it is providing a bound from below, global bound. So geometry is like this way. So you have taken a convex function like this way, and after you know that it is already given the function is first time differentiable, so we can talk about first order approximation of the functions at any point x. So we are taking first order approximation. So if you see this first order approximation, it is talking about tangent to the function at point this, and hence we can geometrically we can see that this function, every bit of this function, it is always above the on and above the tangent plane. So we can say that this tangent plane, it is providing a global underestimator of the given function. So and hence this function is everywhere you observe same kind of situation. It is very much essential to observe everywhere same kind of situation, then we can claim that the given function would be a convex function. Okay, now another criteria is coming from second order characterization. What does it say that? So suppose your function, you are having a function which is second order second time differentiable. So what you do, if it is second time differentiable, easily you can find a Hessian of that function that happens to be a matrix. So find the Hessian and see the nature of the definiteness of the matrix. So matrix, that Hessian matrix, if that Hessian of the corresponding matrix is positive semi-definite, that means there are various approach to define positive semi-definite. If you take a matrix, how we can say that it is positive definite? So in linear algebra class I have already discussed a lot. So there are various sufficient results to describe definiteness of a matrix. So one of them is simplest, that if you are able to find eigenvalue, observe if you are able to observe eigenvalue, then you can say that that what that matrix will sign definiteness of that matrix will be decided by sign of eigenvalue. So here we have taken a triangle matrix, okay, lower triangle matrix, and having diagonal entry 1 and 2. So easily we can see that what are the eigenvalue of this matrix? Call it this matrix A. So what are the eigenvalue? First eigenvalue is 1 and second eigenvalue is 2. So both eigenvalue happens to be positive. So easily we can claim that this matrix is a positive definite matrix. How we define positive definite matrix? That means take a matrix and do define a quadratic uh, form of that matrix. That means x transpose A time x, and this is what it is a quadratic. We call it quadratic function. If this quadratic form, it is always greater than equal to 0 for every x, then we claim that this corresponding matrix is a positive semi matrix. So that is the definition of positive semi-definite matrix. So that's why here if you observe, and how you can directly come to know a matrix is a positive semi-definite, either validate this one or you can see the eigenvalue. So here eigenvalue are positive. All eigenvalue of the given matrix happen to be positive, then you can claim that that corresponding matrix is a positive definite matrix. That means if you define a quadratic form of this matrix, given matrix having this entry, then always I can claim that the corresponding quadratic form would be always greater than 0. It is always greater than 0. So that's why the matrix A is a positive definite. More than semi-definite, it is a positive definite. If I take here 0 in place of that, then it becomes a positive semi-definite. So that is the criteria of defining a positive semi-definite matrix. So here Hessian happens to be a positive semi-definite matrix for a convex function. Okay, so I have taken one simplest example, that this quadratic function I am taking. So here in the quadratic function, it is very much essential that first term must be your quadratic form. So here first term is x transpose px, second term is a linear, and last term is a constant. So it is a quadratic function, what we are calling it. So we are having a quadratic function. So we are claiming that what would be the convexity of this function. So in order to explain about convexity of this function, we have to find Hessian. So it is a simple quadratic function. In Hessian, find the twice derivative of this one. Hessian would be what? Equal to the just coefficient of this quadratic form, equal to p. So we can claim that this function is convex if and only if the corresponding coefficient matrix p of the quadratic term is positive semi-definite. So if this one is positive semi-definite, we can claim that the corresponding matrix would be a the corresponding quadratic function would be a convex function. So it is very easy to test for quadratic function. Quadratic kind of function we can, or those functions which are having a quadratic approximation. For those kind of function, usually we can test with the help of second order characterization. Now I will talk further example of convex function. I have taken it various examples. So one simplest example I am taking quadratic over linear. So these nomenclature are really interesting in order to understand quantity of complicated function in a simple form. So we are having a quadratic in the, you can see that in numerator we are having quadratic term and denominator we are having linear term. So that's why the name of this function you can say it quadratic over linear. Okay. Now we will go. This one is a very nice and a smooth function except y equal to 0. It is nice and smooth. Okay, so what you do, find the Hessian, that second order derivative, find the Hessian, and if you are willing to find the Hessian is taking very simple kind of form. This one is what? It is outer product of the vector y x and first entry is y, second entry is minus y. So outer product of this vector, call this vector A. Say outer product of this vector. If you try to see outer product of any vector, that always happens to be greater than equal to 0. You can test, you can verify yourself. So what you do, take any vector and define the outer product, any vector. Okay, x first entry is x1, second entry is x2, and do outer product. That means x in the vector x into x transpose, that we are calling it outer product. So it is giving a one rank matrix, and apart from that we know that what would be the rank of that matrix. It would be 1. And what would be eigenvalue? Easily you can see that eigenvalue, it would be multiple of 1, it will simply, or 1 or multiple of 1, simply you can say that. So what is that? That would be always a positive quantity. So we can say that this kind of matrix is always positive semi-definite matrix. And hence we can say that Hessian of this function quadratic over linear is a positive semi-definite matrix, and hence we can claim that the given function is a convex function, provided that here there is one more term is coming here 2 by y cube. So we have to also look for sign of the this term as well. So when this will have a positive sign, when we put a condition that y is a positive, here we can't take y equal to 0, otherwise it will be undefined. So we can't take y. So here y must be greater than 0. So for y greater than 0, this Hessian would be always positive, and hence positive semi-definite, and hence we can say that the corresponding function quadratic over linear would be always a convex function for y greater than 0. So plot, you can see it like this is the plot. You can see this is the plot. Easily you can see it like this way. Now I am taking one more example, log sum exponential function. So what does it define? It, the name itself, it says that first log subs, that innermost thing would be exponential, after that log, and outermost would be log. So the log sum logarithmic of sum of exponential. Okay, and here it is very helpful in defining that soft-right function. In software regression you will come to see that. So log sum exponential, it is defined as a logarithm of a sum of exponential, this exponential term. So that we are calling it log sum exponential function. And again this one is a very smooth kind of function. You can easily find the what we call it second order derivative happens to be Hessian. It is expressed in terms of this again outer product is coming. So what is happened that the calculation itself, it says that the Hessian of the log sum exponential function would be always positive semi-definite, and hence we can claim that the given function would be always a convex function. It is a convex function. Plot also you can see it, one plot in case of n equal to 2 I have taken it. So here it is the plot of the log sum exponential function, and it happens to be a convex function. Okay, it is already over 45 minutes. Other thing we will cover in next class. Just one part I will cover here, calculus of, very simplest part, calculus of convex function. What does it say? That if you take any two function and perform a conic combination of those two convex function, then it preserve convexity. It preserve convexity. That means what does it say? That you are taking a function f1 which happens to be convex, and you are taking another function f2 that happens to be a convex, and you do perform conic combination. So what does mean conic combination? I had told that take linear combination of those two functions, but remember that the coefficient must be non-negative. So only this condition we are putting, this condition we are calling it conic combination of f1 and f2. So if f1 and f2 both happen to be convex, then corresponding conic combination is again a convex function. So that, and that conic combination can be generalized. That is coefficient, if you take in continuum fashion, then this become can be written as an integral. Here y is talking about indexing, that indexing we can say that. So or you can take that this multiple that non-negative multiple of f of x in the process of defining convex combination, and the summation will be converted into integration. So we can say that if f of x x y is index, f of x is convex in x, we are just talking about convexity in x. And if you do all possible conic combination for positive this positive weight, then we can say that this integral would be also convex. It is generalized from convex combination. Another is that another example of that convex conic combination of convex function, it is coming as an example log barrier for linear inequality. So take it as a homework and try to see how it is just derived from conic combination of convex function, how you can express this log barrier for inequality as a conic combination of convex function. How you can say that it definitely it is a convex function. It is a convex function. And like one more thing is that if you are taking affine argument of a convex function, then with respect to this affine argument, it is again a convex function. So okay, so this is the end of today's lecture.